So, hello everybody. My name is Douglas Viana Coutinho, and I'll be presenting my master thesis titled Transfer Learning Across MLIR Dialects, which was advised by Professor Fernando Magno Quintão Pereira and co-advised by Dr. Wanderson Martins do Rosário. Thank you all very much for coming. Special thanks to Anderson and Chris for accepting to be part of my defense committee. And special thanks as well to Fernando and Wanderson for supporting me throughout the work. So the presentation has 4 parts. First, I'll talk about the motivation and the problem addressed in the thesis. Secondly, I'll go over the methodology, talking about the transfer learning pipeline that was developed. Third, I present the experimental results, which are organized as a sequence of research questions. And finally, I talk about the conclusions, limitations, and future work. So, machine learning has been applied to compilers for more than 2 decades now. And usually they are there to help compilers make 2 kinds of decisions, basically. One which is what optimizations to apply, and the other which is in what order to apply these optimizations. And in all of this time that machine learning has been applied to compilers, it has evolved quite a lot. Starting in the early 2000s, people were mostly using like handcrafted features to feed classical models so they could make decisions. Then eventually people started using features from the intermediate representation itself, like in the work of Fersen in 2008, where he used these IR features to decide which optimization flags to use. Then eventually the field evolved to apply deep learning and graph-based representations, where even the features themselves are learned, so you don't have to like handpick things anymore. All the way to what is done today, where machine learning is used in production compiler pipelines like LLVM, for example, to make decisions and guide the compiler pipeline. And one requirement that stays quite consistent across machine learning in general, and it's no different when applied to compilers, is the need for large labeled datasets, which is something quite central to my thesis. Now, one very important project in the compiler world that came to exist somewhat recently is the MLIR compiler infrastructure. So MLIR stands for Multi-Level Intermediate Representation, and it allows you to work with dialects. So dialects are defined as these modular sets of operations and types, and each one of these dialects captures a particular domain or level of abstraction. And what you can do is you can mix and combine these dialects to create a pipeline that spans multiple levels of abstraction. And what that means is that the same computation can be expressed in several different dialects, and that computation gets progressively lowered from the high-level dialects to the low-level ones. And it is specifically made to be extensible by design. So you create and change these dialects as needed, right? I have one example here that shows this idea where the same computation fragment in 2 different dialects, stable edge low here on the left and Linaug on the right. You can see that stable HLO has a higher level, more compact representation, while Linaug uses lower level operations that make the structure a bit more explicit. And now, here's the core problem that my thesis is trying to address, which is related to data scarcity and the need of retraining models. It comes from the fact that these compiler models usually need a lot of labeled data available for training. And the problem is that new MLIR dialects, for example, that can get created quite fast, end up not having enough benchmarks built for them. But not only that, these dialects can evolve quite quickly as well, which means that both the data existing for them and also the models that were trained using that data can end up not being fit anymore. So you end up in the scenario where a new dialect emerges or an existing dialect is changed and you don't have proper benchmarks for it anymore, which means you end up with no reliable model that can be applied to them. And that's where the idea behind my thesis comes from. Given that the loading pipeline between MLIR dialects represent the same program and they share a similar structure, would it be possible to transfer the knowledge from a source dialect that has a lot of available data to a target dialect that doesn't have as much data? And what that means is that I can have a one-time pre-training where data is plentiful and only adapted where it is scarce and when needed. So in the example here, I have Stable HLO as the source dialect and Linaug as the target dialect, which is actually the configuration I use for most of the experiments. So this is the entire methodology pipeline for my thesis. The cross-dialect transfer pipeline. The whole idea is to train the model on the data-rich source dialect and then adapt it over the data-scarce target dialect, retraining only the parts needed. So as you can see, both the source and the target MLIR go through a translator, and they get transformed into a ProGraML graph, which I'll go over shortly. But basically, ProGraML is a way of representing programs as graphs. Then a model is trained over the source ProGraML graphs and later adapted over the target ProGraML graphs, where some parts of the model can stay frozen, meaning that information can be transferred without changes. So now going over ProGraML itself, ProGraML stands for Program Graphs for Machine Learning. And it is basically a way of representing programs using graphs. And ProGraML was specifically designed to be fed to machine learning models so we can learn from the programs. The idea is that ProGraML represents the program as a directed multigraph, where the instructions and values in the program become nodes which are connected by different types of edges. So as you can see in the example here, initially I have a piece of seed code that gets transformed into LLVMIR. And from there, the nodes of the graph are created from the instructions and connected by control flow edges. Then the values used and produced by the instructions get added as nodes as well, the red ones that you see, connected by the red edges, the data flow edges. And finally, the call flow edges, the green ones, are added as well to make the connection between functions and the program. And so the program becomes a graph, which is what is fed to the machine learning models. Now, one difference is that the original ProGraML works on top of LLVMIR, but we decided to extract the graphs from MLIR instead. So we needed to develop that tooling to be able to create ProGraML graphs from MLIR. And we do this because that gives the flexibility to extract these graphs at various levels of abstractions, compared to LLVMIR, which sits fixed pretty much at a low level of abstraction. So I just have a quick comparison here of what happens to some constructs when you convert them to LLVMIR and MLIR. So loops, for example, get lowered to branches and comparisons in LLVMIR, while in MLIR they can stay as first-class operations. Tensors get flattened to pointer arithmetic in LLVMIR, while in MLIR they can get preserved. And domain-specific operations, for example, convolutions and whatnot, get lowered away in LLVMIR, while in MLIR they can be retained as named operations. Now, I just have a quick table here basically showing how some MLIR concepts map to ProGraML. So basically an operation in MLIR becomes an operation node or an instruction node in ProGraML. An SSA value becomes a value node, and an attribute, an operation attribute, becomes a constant node. And another difference as well is that MLIR has nested regions. So I basically do a recursive traversal to handle these nested regions, basically flattening the MLIR structure onto a ProGraML graph. And this tooling, this conversion tooling, is open source and is available at this repo right here. Now, talking a bit about the model itself, the neural network used in the thesis is a GNN, which stands for Gated Graph Neural Network, as you can see here. And the architecture can be separated into three components, basically. The first one are the node embeddings. Here, basically, a vocabulary is created from the dialect in MLIR, and each one of the nodes in the graph gets assigned an initial state depending on the vocabulary here. The vocabulary maps the node type to the embedding table. So each node here in the graph receives a embedding depending on the lookup table. Then there's the message passing component in the middle. This component is basically like the heart of the GNN, and it's a process where nodes repeatedly exchange information with their neighbors. And there are a few important parts here. One is the position multi-layer perception, which basically helps the model differentiate between the positions of arguments in a function or an operation or something like that. Then there is the edge transformation, which basically helps the model understand the type of edge connecting two nodes. And then there's the GRU, which is the gated recurrent unit. And this one right here basically modulates how much of the current node state gets changed when new information comes in. So that's the message passing component. And then there's the final component, which is the readout, which basically pulls the final states in the graph into a prediction, in this case, a scalar prediction. And this is basically the whole model, how the graph model works. Now, one question about the architecture is which components can actually transfer information between dialects. As I said, the architecture can be divided into three different components. The embeddings are dialect specific, so different dialects have different operations, so this part needs to be retrained. The readout usually helps recalibrate the network to a new domain, so it needs to be retrained as well, or at least that's the assumption. And the message passing layers, though, learn how information flows through the graph, which is like general structural knowledge. So the hypothesis is that the message passing layers capture structure that can actually be transferred across dialects, while the embeddings and the readout have to adapt. So the experiments are designed to test this hypothesis that some parts of the message passing component can be kept frozen and still be useful when adapting the model over to the target dialect. So to test the hypothesis out, the idea was to run 8 fine-tuning configurations that cross two factors independently. So the first one is progressive unfreezing. As you can see here, I have the parts of the message passing component. And starting from everything frozen in the message passing component, I unfreeze some parts one at a time. So I start with everything frozen, then I unfreeze the GRU, and so on. And the second factor is how the embeddings are initialized. So either randomly or from the mean of the source embeddings. And you'll see like the difference between the experiments 1 through 4 and 5 through 8 are just the initialization. So experiments 1 and 5 both freeze the message passing component completely, and the only difference is that 1 gets initialized with random embeddings and 5 gets initialized with mean embeddings. And the idea is that I'm going to train a model over the source dialect, and then when adapting the model over the target dialect, I'm going to run these experiments right here. Now, talking a bit about the experimental setup itself, the dataset used is the NASBench dataset. It basically has more than 400,000 neural network architectures and metrics about each one of them as well. The tasks, I'm basically training a model to predict the training time and the test accuracy of these neural network architectures right here. The split used is I take 90% of the data set as stable HLO to be used as the source dialect, and 10% of the data set as LINAUG to serve as the target dialect. And just some information about the GNN model. It has roughly 62,000 parameters, and I use 30 message passing iterations. So before I go to the fine-tuning experiment themselves, there are two research questions here which are important. The first one is about zero-shot transfer. So the idea of zero-shot transfer is to apply the model trained on the source dialect directly over the target dialect without any vocabulary changes or any sort of adaptation. But the thing is, this approach pretty much just fails. I'm not going to go into too much detail here. But like, as you can quickly see in these columns right here, zero shot and zero shot here, the zero shot transfer just does not provide much meaningful results. So the takeaway is basically that direct transfer fails and some explicit adaptation is required. Now, the second question is about data efficiency, and the idea here is to measure training from scratch on the target dialect to see how the accuracy evolves as the data set size increases. Now, for the majority of the graphs that I will show, they follow this format right here of showing the training progression over the epochs and the correlation metric, which is Kendall's tau. Kendall's tau is a ranking metric that basically measures the ability of the model in ranking neural networks appropriately. And here you can see the progression as the amount of data used for training increases, starting at 1%, where the model doesn't perform very well, and then 5%, 10%, 15%, and so on for both training time and test accuracy tasks. And basically, the higher the amount of data, the better overall the model performs. So the takeaway is that training from scratch requires high amounts of data for competitive performance. You can't just use 1% if you really want to reach those higher levels of model quality. Now, for research question 3, this is one of the main questions of the thesis, and the idea is to basically compare the fine-tuning approach against training from scratch only NALG. For that, I chose one of the 8 configurations that I showed before. In this case, it was FTE6. And so, as you can see, I have a comparison here between fine-tuning and training from scratch using 1%, 5%, and 10% of the data. So first, for 1%, in black, I have training from scratch, and in orange, I have the fine-tuning. So you can see that in both cases, the fine-tuning performs a little bit better. Then using 5% of the data in blue, I have training from scratch, and in yellow, I have the fine-tuning. And comparing the 10% in green, I have the training from scratch, and in pink, I have the fine-tuning. So as you can see, like, the takeaway here is that transfer learning consistently performs better than training from scratch when using the same amount of target data. Now, for research question 4, this is a very important one as well, and it is about architectural plasticity, which is basically how does the model behave when we freeze different parts of the message passing mechanism. In here, I have all of the fine-tuning configurations that I showed before. First, the training over the source dialect in stable HLO. So you can see here in black where I do the training over stable HLO, which uses 90% of the data set. Then I have the training over LNALG only using 10% of the data set. So immediately you can already see like the difference between training with a lot of data and training with not so much data, right? There's already a huge gap here in quality by just using more data. And then there are a few interesting comparisons. I think the main one is like experiment 1 and experiment 5 are the two experiments, the two configurations that completely freeze the message passing component. And as you can see, they do not perform very well, especially right here. This one, it even performs better than the Scratch, but it still does not reach the other configurations right here. And this one performs very, very poorly. And the idea is that freezing the entire message passing component is not ideal. It's not very good. Compared, for example, to the other fine-tuning experiments like 2 and 3 and 6, where they only partially freeze it or don't freeze it at all, where the performance is just straight up better. So basically, the takeaway from our research question 4 is that it is better to just only freeze the edge and position multi-layer perceptrons and retrain the gated recurrent unit, the third part of the message passing component, and retrain as well the embeddings and the readout multi-layer perceptron. Now, for research question 5, this one studies how the embedding initializations impact the model quality. So right here, I have a few comparisons as well. First, again, experiment 1 and experiment 5. I'm not sure if you guys remember, but like the only difference between these two is the initialization. Experiment 1 initializes the embeddings randomly, while experiment 5 initializes them with the mean of the source embeddings. And that is enough for training time for experiment 5 to do a lot better. For test accuracy, not so much. They pretty much achieve the same quality. Now for experiment 6 and experiment 2, experiment 6 using the mean, here they kind of get to the same place, and here experiment 6 mean initialization wins. Here they get to the same place as well, while in here mean initialization wins again. And in this case, experiment 8 against experiment 4, mean initialization wins against both cases as well. So the takeaway is that mean initialized embeddings provide low-cost stability gains. Now, going for research question 6, the idea here is to compare fine-tuned models against models trained from scratch regarding time efficiency. Before that, though, I have a comparison here that shows the time per epoch when you train over stable HLO in black compared to LINALG in orange, using the same amount of data. And the conclusion is basically that training over stable HLO is cheaper than training over LINALG. Sorry. Now, here I have two tables comparing the time to train of a specific fine-tuning configuration against training from scratch. I know this is a lot, like there's a lot here. I'm not going to go into too much detail. I'm not going to go over it too much. But the overall takeaway is that fine-tuned models not only achieve higher accuracy, but they also converge faster. And especially when you consider that the time spent on pre-training can be considered an offline one-time cost that is going to be amortized over all of the adaptation runs that you're going to do. There's a very clear advantage in applying fine-tuning. Now, for the last question, research question 7, it asks whether the approach generalizes beyond LINALG. So by transferring from stable HLO to other dialects. The first one that I used is a combination of dialects, actually. It's namely, it's SCF, MEMREF, and RIF. And this combination basically sits a bit lower than LINALG in terms of abstraction level. It goes beyond LINALG. And the conclusion here is that there are still some gains from applying fine-tuning, especially in the task of predicting test accuracy, but the gains aren't as pronounced as when adapting to LINALG. And then I also ran the same tests for LLVM-IR as the target dialect, which sits at a very low level of abstraction. And here there's way less gain from applying fine-tuning, where training from scratch pretty much performs the same as the fine-tuning configurations. So the takeaway is that transfer is more efficient at smaller dialect distance, and the performance degrades as the dialect distance grows. So a summary of findings, these are related to each research question basically. So the first one is that zero-shot transfer fails and explicit adaptation is required. The second one is that training from scratch on a new MLIR dialect is highly data inefficient. Third is that transfer learning outperforms scratch training. Fourth is that selective freezing matches and often performs better than full fine tuning. Fifth is that smart initialization provides low-cost stability gains. Sixth is that transfer can considerably reduce time to solution. And seven is that the effectiveness of transfer degrades with dialect distance. And now the main contributions that I think the thesis offer. The first one is the cross-dialect transfer learning pipeline as a whole, like the whole methodology for repurposing machine learning models across MLIR dialects. The second one is the architectural decomposition, is identifying which GNN components actually encode universal versus dialect-specific knowledge. And third is the tooling, basically the entire open source toolchain, especially the converter that allows you to create ProGraML graphs from MLIR, and the entire machine learning pipeline as well. Now, for some limitations, one is that the work only uses a single benchmark suit, like I said, the NAS bench dataset. Another one is that we only deal with prediction tasks, so we haven't actually applied the pipeline to optimization decisions inside the compiler yet. Another one is that we only use a single source dialect, which is stable Jalo, and it also has limited dialect combinations. Another one is this fundamental boundary where dialect distance can make the transfer not very effective. And the fifth is there's no formal metric for this dialect distance, so you can't really know in advance whether, like, what to expect if the pipeline, if the methodology is going to be efficient or not. So given that, I think some future work could be, the first one is to apply to downstream compilation tasks like tile selection, scheduling, actually applying it to a compiler. Another one is multi-source transfer across the lowering chain. So not necessarily using just one source dialect, but multiple. Another one is software adaptation like EWC or adapters for more distant dialects instead of just straight up like freezing certain parts of the neural network. Fourth is to formalize dialect distance as a predictive metric so people can actually have at least some idea whether or not the approach is going to be effective. And lastly, cross-domain transfer beyond the lowering pipeline, which is basically testing out if the pipeline works among two dialects that actually don't have lowering between them. And that's it. Thank you very much. Thanks again to my advisor and co-advisor. And I'm open for questions.